Hello, everyone. Hello, everyone. Welcome back. Welcome back to Calculus 1000. Today, we are going to start a new topic, which is basically the first thing we need to know when we are trying to sketch the graph of function. And this will continue for a bit. We will try to learn a few more things, increasing, decreasing, concavity upward, concavity downward, different tests. And the goal is by the end of 4.4, I believe, we have enough tools that if someone gives you a function, you can basically start, do some work on it, and sketch the graph of that function. We specifically today are going to focus on local extremums, and we want to understand what are these things, what is the definition, what we know about them, and then we will move to something called critical points, and we will try to learn a bit more on that line. Is there any questions, any comments before we start? Yes, please.
The midterm, right?
Midterm, okay, so this is a good question for me to make sure that I announce this another time, that the midterm content for our section, if you attended our class, will be all the way to the end of implicit differentiation or whatever we covered before the reading week. I cannot say about other sections. They may have something left for last week. The exam is going to be the same thing. It is going to cover all the way to the end of implicit differentiation. There is only one 4.6. Remember the limit at infinity? We covered it when we were studying limits. That's also, if you're going to go like section this, 4.6 is also included. In other words, none of the content that we are covering this week, nor the ones that we did last week, will come in the midterm test. That's what it is. Any other questions? Any other comments? Can we start then? Are you ready to start this? No, you're not, yeah? What's happening? Are we all feeling okay? No? What makes you worry? Don't say it, I know. Now, okay, let me just tell you one more thing. Maybe this will help you a little bit. So I'm trying to do at least one, hopefully two review sessions this week. And hopefully this will be done on Thursday and Friday. So basically we will stop whatever we cover up until Wednesday. That's my plan if everything goes well. And then Thursday and Friday we will go quickly over some sample questions or some review content. So just keep in mind that we will have. Today you don't want to listen to me. It seems, yeah? Okay, I'll play that way today then, okay? Okay, let's start with local or relative max and min. The hope is to identify, to learn the definition and try to apply it. Let me start with let me start with max, and then min will go the same way. So definition, we say f has a relative or local, let me write both, relative max or local max at a given point C if it is maximum value, if has maximum value. In other words, if at C is bigger than or equal to f at x. But for what x's? This is very important. What x's basically fixes what does local mean. When we are talking about local or relative, what we are interested in around that point. So for all x's around x, or maybe near x. So in other words, when you focus around that point, the value of the function at that point is bigger than or equal to any other value around for all other values. The minimum is defined same way. So note that. So we say, okay, let me write this. We say f has a relative min or a local. Those are the same equivalent things to say. Min at C if at C, the value of the function at that point is less than or equal any other value. Any other value for all x's near C. Or for all x's near C, not near x. Understanding local has, you can basically go ahead and try to use these examples because you know graphs of some functions. You can easily identify local max and min. Identify local max and min values. So I'll draw you a graph. So this graph comes up, so -1, -2, -3 is here, and then goes down there, up somewhere here, and then that's the hole there, and this comes from here. Two. 3, 4. Okay. Let's work on this. You need less than 1 minute. If you understand what is the definition of local max and min, you basically need 45 seconds. I'll give you 1 minute. Feel free to talk to the friend sitting next to you. You don't need to sit there quiet, not doing anything. You need to talk to someone and make sure that you kind of start examining this. Let's go ahead. 1 minute starts now. seconds left. Please talk to someone.
Actually paying attention.
Okay. Let's see for the local min. Can I hear how many local mins you're finding there? Yes?
X equals 2.
So x equal to 2. This is the point that the function goes down and function at that point seems has the smallest value. So f has relative min values or value at first x at 2. What else? Relative or local min. What other points? Yes, please. At negative 2. Yes, just note that here, again, when I'm looking at the whole domain, there are values less than this. There are values less than this as well. But when you're talking about relative or local max and min, you don't need to check every other point. You see this point, go around this point, ignore the rest. Near this point, it seems that the function has smallest value at negative 2 as well. So at x equal to negative 2 as well. What else? What other point? Are we all good to say that's all we have? Yeah? Okay. How about f has relative max values at what points? What points? Yes, please. Negative 3. When we look around negative 3, okay, it seems that, yes, the function is getting the highest value. I'm trying to do this. And yes, so f has relative max at negative 3. How about 0? How about 0? One thing that you have to note here is that maybe if you look only one-sided, yes, f at 0 on the positive values close to 0 has greatest value. But when you're checking local max and min, you have to look at both sides. And when you go like this, oh, look, this value has bigger than this. This is bigger. And unfortunately, the point over there is not the solid point. So the value of the function is down here. These guys are all bigger, never reach the highest value. And f at x at 0 cannot give a local max. And the same story would go for, say, this is 3, this is 4, for the value of the function at 4. Can you say something? Obviously, x equal to 4 doesn't give us local max. How about local min? Do we have local min at that point? Look, if I restrict myself here around 4, what is the smallest value of the function that you can see there?
0.
At 0. Everything is positive bigger than 0. So x equal to 4 also gives us another local min. Because around 4, when I look at it, the value of the function is the smallest. Okay? these points, the way you write it is very important. When you want to write x values, you have to say it this way. If you want to say f has local max values, in that case, what we are looking for is what is f at 2, f at -2, and f at 4. When someone is trying to ask you value, then you have to plug into the function. But when it comes to number or point, we are talking about the x value. So then you can plug it in. For example, f at 4 is 0, f at -2 is 0, and this guy is, say, -2, something like that. What we learn from this example, first of all, local max and min really matters the way it is defined. You're going around that point and forgetting everything else. That's by definition. The second thing that you have to note here is that to be a local max or local min, your function doesn't need to be even continuous at that point. This definition has nothing to do with continuity or differentiability or anything any other regularity conditions. The definition just goes based on the values. But we will see that something related to that will come up. But before that, I want you to go quickly through some examples that you already know how to graph, and quickly tell me what are the local max min values of those functions. So this is another example. Find local max min values of given functions. First one, oh, our friend, the parabola. The second one, quadratic function. You know the graphs of these guys, so I'm expecting you to quickly tell me where are the local max min. F of x is sine x, and the fourth one is f of x is secant x. Go ahead, I'll give you 90 seconds, and here what I'm expecting you to do is that sketch the graph and quickly based on what you can do with the graphs, identify at what points we have local max, local min. Yes, please.
For the board on the right, you were talking about when you said values, you're looking for f at point. Why does it also say values on like the top two?
No, the value over there, we are saying that f has relative max min value at a given point. Okay. Yes? And yes, that's the difference. Okay, go ahead. I give you 2 minutes. You're quickly sketching. You can talk to the friend sitting next to you. Try to convince them or convince yourself why are those points the critical, the local max or local min for those given functions.
Yes.
I was like,
Actually, no, yeah. Like 8.
no, one. It's gotta be wrong.
One minute left. Okay. You know the graph of this function. This is the standard parabola. And you can see, or you already know that x squared for all the values of x are bigger than or equal to 0. So then f has a local min at 0, and the value of that is 0. Yeah? Do we have local max in this case? No, as we go higher, as we go to the right and left, the values of the function goes higher and higher. No local max. X cubed, we know the graph of this guy. Yeah? So this function, did I draw? Kind of. Well, at that point, it must be 0. My function is not a very 0 on the tangent, the line slope. But we know that the more we go to the right, the higher the values go. The more we go to the left, the lower the values gets. Yes? So that means that we don't have no local max nor local mean. Yeah, the function can have no local max, no local mean. When you look at the function sine x, you know it goes periodically, and we know that the highest value the function gets is 1. So local max value is 1, and happens at what points? At pi over 2, 3 pi over 2, then 5 pi over 2, and so on. In other words, in all the odd multiples of pi over 2, this, only on the pi over 2 or 2 pi plus multiple pi over 2s this happens. So it happens at x equal to multiple of 2 pi plus pi over 2. Yeah. Local mean, we also know, is -1 for sine function, and happens at what points? Happens at x equal to, well, basically the multiples of 2 pi plus 3 pi over 2. So you add those ones and you get all those values. How about secant? How about secant? What are the local max values for secant? Yes?
It'll be the
Are you using the graph, or what are you using there? Can you tell me?
I have the graph, but I'm just...
You have the graph. Let us see if we can sketch the graph here. Secant x is 1 over cosine x, and the way it will work is that you're inversing cosine values. For example, if I go at negative pi over 2 to pi over 2, at these 2 points, cosine is 0. So these are vertical asymptotes, and this repeats itself. Now, remember, cosine itself is of this form. If you find the inverse of that, it will go like that. And then you repeat the same process. Now, let's see where we are getting local max. This is local min. This guy is local max, local max. They are happening when cosine of x is -1. 1 over -1 is -1. So local max values are 1. Where do they happen? They happen when look, well, I'm looking for -1 here, for example. That is when we have pi. Then you go 2 pi there, there's 3 pi, 5 pi, and so on, and you got the negative. So happens that x odd powers of pi. Sorry, odd multiples of pi, or pi, add any multiple of 2 pi to that. Local min values are -1. And they happen at these points, happen at x is 2 even multiples of pi. Yes, please.
Would it be -1 for max and 1 for min?
Let's look at this when only we focus on this intervals that can show up here. When you look at this point, which is what? This is -pi, yes? When you look at the values of the function around pi, this guy is the highest value. So -1 is local max. Because when I focus around that point, it shows the highest value. So, oh, I'm saying it and wait. You're right. Sorry. I thought always I'm writing the positive -1, right? You're right. -1s are local max values. Positive ones are local min values. Thank you very much. Thank you. Yeah. Well, the functions get more complicated. We have more things to do. Yes? Now, the goal is to figure out how a function can have a local max or local min. And here is where this important fact comes in. Let's just focus on local max thing. For example, we already seen something like that could be local max, or something like that. Something like this could be local max. But once it is continuous, there is no other way than having that shape. So if your function has a tangent line at that point, or it is differentiable, let me tell you this way. If it is differentiable, to be local max, it means that the values before that and after that must be all less than, and this is the only possibility. And what we learn about those cases is that if the function is differentiable at a local max point, the tangent line to that point is going to be horizontal. Or in other words, f prime must be equal to 0 at that point. This is what's called Fermat's theorem. If f has a local max or min value at C if it has local max or local min value at C, and f is differentiable at C, then f prime must be equal to 0. The tangent line to the graph of function at that point must be horizontal. Then f prime must be equal to 0. Other way of writing Fermat's theorem would be this, that if f has if f has a local max or local min at C, then either f is not differentiable at C, or if it is differentiable, its derivative must be equal to 0. So what it does is telling us that there are only two possibilities at which local max and min can happen. We take these two conditions, we call these ones critical points of f. Critical points of f are points at which either the function is not differentiable or it is differentiable and the derivative is equal to 0. And we will I'll keep this one as remark. Critical points are candidates for points at which local max or local min happen. They are candidates. Can anyone come up with an example or two examples that a point is a critical point, but it is not a local max nor local min? I want to say that the inverse of this thing is not true. We may have critical points that are not giving us local max, local min. I'll give you 40 seconds. You're talking to your friend, and I need you to come up with two examples. One, where f prime is 0, but the function doesn't have local max, no local min. The other one is f prime is not differentiable, and the function doesn't have local max, local min at those points. Two examples, 45 seconds. You're trying to find functions with critical points without local max, local min. Go ahead, please. 45 seconds. Okay. I want to hear the examples. Yes, please.
F of x equals x cubed.
X cube is a nice example. Why? Because if you, first of all, it is differentiable everywhere, yes? If you find a derivative and set it equal to 0, you see that 3x squared must be equal to 0. So x equal to 0 is a critical point. Yes? But we just talked about that. At 0, the graph goes like this, but it doesn't introduce any local max nor local min. Indeed, x to the power 3 doesn't have any local max and local min, even though it has one critical point. How about another example that, yes, please? Tan x. What are the critical points of tan x? Tan x is a little bit complicated case, yes? So function is not defined at the bad points. But do you have any other example that the function is not differentiable at point, but it has a critical point at
Inverse.
Inverse of cubic function. What is the inverse of cubic function? Third root? Yes, isn't it? Third root of x is not differentiable at 0. Well, it has vertical tangent line at 0. We did this example before. So it's not differentiable at 0. So x equal to 0 is a critical point, but the function third root of x doesn't have any local max nor local min. Yes? So critical points are candidates of being local max, local min. They are not giving us local max and min all the time. There are cases. These are the examples. Yes, please. Ln x. What are the points for ln that are not different? What are the critical points of ln x? 0? But ln is not defined at 0, yes? Yeah, so it's outside of the domain. Well, I mean, you could do absolute value of x actually here. Yes? Absolute value of x is not differentiable at 0, so x equal to 0 is a critical point for it. But, oh, that's a bad example. Oh, that's bad. I want to say, I had this in mind. I said absolute value. If you sketch that graph again, it has like a corner at 0. So 0 is a critical point for it, but it doesn't have any local max nor local min at that point. Okay. So I'm hoping that at this point you see the critical points are not going to give us all the local points, but we know that local max and local min will happen definitely in some critical point, if there is anything. So finding critical points is important for us because that way we are gathering some candidates for local max and min. And what we will do next is another story that will come maybe on Wednesday or next week. Let's try to do some examples for critical points. Find critical points of all the critical points of the given functions. F of x is 2x cubed minus 3x squared minus 36x plus 20. Why not? F of x is x plus cosine x. The other one is ln of x squared minus 1. Go ahead, please. I expect you to be able to do at least 2 of these questions in the next 2 minutes. We are looking for critical points, means that you're trying to identify 2 types of points. Where the function is not differentiable, where it is differentiable and the derivative is equal to 0. Okay? Go ahead, please. 2 minutes, and I'll do it on the board after that.
Okay, that way no job. I have that on my resume. Wait, I want more free time off, so that's my time. Wait, how do you like do syntax? Is it just like you have to write? Like what part of this code is wrong?
You have 1 minute left.
Oh, there's 2 lectures. And then you have a tutorial. The 10:27. I have a tutorial that I have to do. Okay, I might switch to in person. Oh wait, we should do a content together. Coffee chats have you been? I do. That's so much.
When someone is asking you to find critical points, you first ask yourself, is there any point at which this function is not differentiable? Here, this is everywhere differentiable, so we don't have any critical point of type 1, the ones that is not differentiable. So no critical point at which f is not differentiable. Because this is polynomial, it's everywhere differentiable. Now, we want to go for the other type of critical points, where the function is differentiable and the derivative is equal to 0. So we have to find the derivative here. This is 6x squared minus 6x minus 36. You find the derivative, set it equal to 0. Then I can factor out 6 and I get 6 squared minus 6 minus 6 equal to 0, yeah? And I'm looking for two numbers which add up. Which add up to -1, so that's x minus 3, x plus 2, and when you multiply, you get -6, yes? From there, you get x equal to 3 and x equal to -2 are two critical points of these given functions. Yeah? How about this one? This is again everywhere differentiable. So the only critical points will happen when f prime is equal to 0. But f prime here is 1 minus 2 sine x. This must be equal to 0. That means that sine x must be half. Yeah? So then what are the points at which sine is 1 over 2? That is pi over 6 or 5 pi over 6, yes? Also, any of these ones, when you add to a multiple of 2 pi to that, integer multiple of 2 pi to it, then you will get all the critical points. For the last one, when you're doing the derivative, be careful here. Ln of something, the input for ln must be positive. In other words, domain of this function is all x's such that x squared minus 1 is bigger than, not even equal, bigger than 0. And if you solve that, this is the sine table you plug in there, you get negative infinity to -1, open 1 to plus infinity. That is the domain. So critical points are only happening on the domain. On all the domain, this is differentiable, so we have to set derivative equal to 0. Derivative of ln u is u prime over u. This is f prime. And that is 2x over x is, oh, this is minus. Yeah? This is x squared minus 1. This must be equal to 0. But from that, I can conclude that x is equal to 0. Is x equal to 0 a critical point for this function? It is not in the domain. This is just a funny thing happening because of this general thing. X is not, where did I throw that? I got excited and I throw my chalk. So is not a critical point because it is not in the domain. So just be careful when you're doing those calculations. You have to make sure that your critical points are in the domain. Have a great day. See you all on Wednesday.